Hi there. Welcome to the lesson summary for this is going to be lesson 7.1. Similar triangles. So we're actually launching into trigonometry, but in order to understand trigonometry, we kind of have to do the greatest hits of similar triangles. And so the first thing that we did for the do now that I'm going to cover in this video was just refreshed our memories on how to solve a proportion. And that's really, these two fractions are equivalent to each other. So 5 over 3 is equal to some number over 75. And we talked about how to solve that in class. And a lot of students said, well, I know that 3 times 25 is 75. So x must also be 5 times 25. And it is, in fact, that, which is 125. And you could do the same thing here, kind of thinking, well, I know that 8 times 7 is 56. And so 7 times 7 is x. And so x is 49. And, well, I know that 4 times 18 is 72, or I could say 72 divided by 18 is 4, so 90 divided by 18 is 5, and so x is 5. But I also had to make the point for everybody, and I'll just give you the really easy example that I often give. When you have two equivalent fractions, 2/3 and 4/6 are equivalent, if you do this thing called a cross product, so if you multiply the denominator of one side by the numerator of another side, 3 times 4, that's 12. And if you do that with the other two values, this 2 times 6, that's also 12. So when you have a proportion, you can use the cross product to come up with a new equation that you can then solve. So let's take that to number 1 here. If I do the cross product, I would do 3 times x is 3x, and then I would do 5 times 75 is 375. You can check me. And then if you just divide by 3, then that means x is 125. And so using that cross multiplying and then solving the equation with division is a really, really effective way to solve these problems. Because some of them you can't solve in your head quite so easily. So 4 times 90 is 360, and 72 times x is, of course, 72x. And then you just divide by 72, and you get x equals 5. So you might want to try that on number 2, but let's move along. The next thing that we did in class was I gave everybody this pink triangle here, and I said, find the lengths of A, B, and C. And quickly now I can see that A is 2 and B is 3. And then C here, I would have to use the Pythagorean theorem. So 2 squared plus 3 squared equals C squared. That's 4 plus 9 equals C squared. And so C squared is 13, and therefore C is just the square root of 13. And so we just called it root 13. And what we did next was because we have to learn about these similar triangles, which is related to special right triangles. So what we did was we looked at this thing called a dilation, and I gave everybody this thing to goof around with. And notice that I can change this dilation factor, and it's creating a copy, only the copy is a different size. But I want you to notice a couple things. When I dilate this triangle, the angles are the same. So I have I can't drag them, huh? I have a 56.3 degree angle, a 33.69 degree angle, and then a 90 degree angle. And it's the same in these other triangle, in the original triangle. And I can change other things about it, like so. I can also change the center of dilation so that the new triangle, surrounds the old triangle. And also notice that when the dilation factor is less than 1, then I'm actually, instead of making a larger triangle, I'm making a smaller triangle. But when you dilate a shape, you create a similar shape. It's a different size, but it's the same shape. We even did negative dilation factors. But notice that the angles are always the same. And so the next thing I did was I said, reset it, set your dilation factor to 2, and now find the lengths of the new sides of A prime, B prime, and C prime. And so you can just tell by looking that A prime is, it's 4 units. C prime is 6 units, and so if we do 4 squared plus 6 squared equals C squared, that's 16 plus 36 equals C squared, or 52. And so C is the square root of 52, which a lot of folks got there, but then notice that if you didn't know it already, 52 is 4 times 13. And so we can split it into the square root of 4 times the square root of 13, which is, of course, 2 times the square root of 13, because that's the square root of 4. And so we figured out that C is 2 root 13. So what I want to highlight for you is that with a scale factor of 2, the This side A, was 2 times the original value of 2. This was 2 times the original value of 3. And this was 2 times the original value of the square root of 13. In other words, the three sides of the blue triangle are just double the length of the three sides of the pink triangle, and that is with a scale, or a dilation factor of 2. And if that dilation factor was 3, you could bet that these would all be triple that length. And so that's a couple things I really wanted you to note about similar triangles. The angles are the same, okay, but the sides are proportional. And so then we went on and I gave everybody these notes. They're posted on Schoology. We already know about congruent triangles. They're just the same size and shape. So all the angles are congruent in congruent triangles, and all the sides are congruent in congruent triangles. But then I wanted to note that now with similar triangles are the same shape, but it says usually a different size. Because technically, if triangles are congruent, then they're also similar, right? If they are not dilated at all, they're just the same triangle. But so really, though, let's just think of similar triangles as being the same shape, but a different size. And if they're the same shape, then that means all the angles are always congruent, but the sides are now, instead of being congruent, they're proportional. And so this says, for instance, that, side AB over side XY, if I do AB divided by XY, I'll get the same value as if I do BC divided by YZ, because those are corresponding sides. And if we want to go back and look at the examples that we did up here, taking, for instance, side A was 2, and side A prime was 4. Side B was 3, and side B prime was 6. Those two proportions are equivalent. And in fact, we could do side C was root 13, and side C prime was 2 root 13. All of these fractions are equal to 1/2. And that's because the pink triangle is 1/2 the size of the blue triangle. And if we flip them all, then it would be reversed. And so you have this proportional relationship as long as you, compare corresponding sides between similar triangles, your fractions will always be equivalent, even though the sides themselves are not equivalent. And then we did 2 examples here. So let's do example 1 first. Notice that these 2 triangles are similar. And the reason I know is because they have 3 angles that are all the same. And what we do is we call that angle similarity. All right. And I'm not going to test you on this year. In other years, we would have talked about how to prove that these triangles were similar, but we just don't have that kind of time. But if you know that all 3 angles of one triangle are similar to or are congruent to all 3 angles of the other, then that means the triangles have to be similar. Okay, and that means their sides are proportional. And so the next thing is to say, well, can we set up a proportion to solve these triangles? So this side 24, it corresponds to this side X. And when I set up this proportion, it doesn't actually matter how you do it. I'm just going to do the big triangle over the small triangle like this. So I know that 24 and X are corresponding sides. So I know that if I set up a ratio, 24 is to X. I know they're corresponding because 24 goes from the 52 to the 25 degree, just like X does. Well, I can do the same thing. I know that the 16 side corresponds to the 12 side, so I can set that equal to this other fraction. And I know that these 2 fractions are equivalent. And then you can solve this in any number of ways. I know, for instance, that 16 is 2/3 of 24, and so I could figure out, well, what number is, if 12 is 2/3 of that number. But just for the ease of demonstration, I'm just going to do this cross product thing. And I know that I'll get 16 times X, and then 24 times 12 is 288. And then if I just divide both sides by 16, you can check it with a calculator, but the answer you get is 18. So it turns out that this side has to be 18 units long if these sides are proportional, right? So, and think about it this way, 12 over 16, that's 3, if I divide the top and the bottom by 4, I get 3/4, right? That's 3/4. And if you do 18 over 24, that's also 3/4 if you divide the top and the bottom by 6. And so what that tells me is that this triangle is 3/4 the size of this triangle here. Okay, that's the dilation factor was 3/4. Let's do one more. I'll just skip example 3, but example 2, it says, first of all, how do we know these triangles are similar? And the things to look for here is there's these parallel lines, and parallel lines should make us look for alternate interior angles. So I know those angles are congruent because they're alternate interior angles. I know those angles are congruent because they're also alternate interior angles. And then we also have these vertical angles here that are congruent. And so I know that all 3 angles in the triangle on the left are congruent to all 3 angles in the triangle on the right. And so I could say, for instance, if I was going to try to explain this, I would say like alternate interior angles and vertical angles lead us to angle, angle, angle similarity. Okay, that's how I know that the triangles are similar. And then I just have to set up a proportion to figure out the length of x. And so I'll just kind of follow the same process. I'm going to do, just for the fun of it, this time I'll do small over big. Okay, so we'll do the small triangle on top and the big triangle on the bottom. And I know that this side with the 20 corresponds to this side with the 30, because it goes from the blue angle to the red angle, and this goes from the blue angle to the red angle. So I'll do 20 over 30, and I'll set that equal to the other small side is this x over the large side, which is 24. And then we can solve this. And in fact, it might be easier if we just cancel these zeros out. 20 over 30 is just 2 over 3. And so I can finish this off by doing that cross product thing again. So I'll do 3 times x, that's 3x, and 2 times 24 is 48. And if you divide by 3, you get x equals 16. So this side here is 16. And the last thing I want to show you is that you can also compare the ratios of 2 sides in a triangle. So if I compare 30 over 24, that would reduce to, they both divide by 6, so 5 over 4. And then I could do the same thing here, since I know this is 16. I could compare those 20 over 16, because those sides are part of the same triangle, and they're corresponding, right? So 20 over 16 will also give me, if I divide the top and the bottom by 4, 5 over 4. So that's another way that you can compare the sides of similar triangles. Although for now, you may as well just do small over big or big over small. So please try the exit ticket after you watch this video, and then come to class ready to learn some trigonometry next time.